Have you ever looked at a video of a tornado and just thought, how? How does the air we breathe, something that feels like nothing, turn into one of the most powerful and destructive forces on Earth? Well, today we're going to break it down. We're diving into the incredible physics of how simple air becomes a weapon.
I want you to just look at that number for a second. 300 miles per hour. That's over 480 kilometers per hour. That's the fastest wind speed ever clocked inside a tornado. It is pure, focused, terrifying power.
So that's the big mystery we're tackling, right? How in the world does the atmosphere organize itself into something so incredibly violent and focused? It feels like it shouldn't be possible, but the answer is just some really, really elegant physics.
All right, before you can even think about a tornado, you need the right kind of storm. And not just any storm will do. You need a monster, a rotating behemoth called a supercell. And getting one of those requires a very specific and very volatile recipe. It really comes down to these three key ingredients. You've got to have that warm, humid air down low. Think Gulf of Mexico. Then, way up high, you need some cool, dry air. When those two meet, you get instability. But the real secret ingredient, the one that gets everything started, is wind shear. This is the magic element that introduces the spin.
Okay, so we have the ingredients for a massive storm. But a storm isn't a tornado. Where does that iconic, terrifying rotation actually come from? Well, it starts long before you see any funnel cloud. It actually begins as an invisible spinning motion high up in the sky.
It's basically a three-step process. First, that wind shear we talked about creates a big, invisible tube of air spinning horizontally, like a log rolling on the ground. Then, a powerful force from the storm lifts that spinning tube up and tilts it so it's vertical. And finally, and this is the critical part, that vertical column of spinning air gets stretched and squeezed, which makes it spin violently fast. Let's break that down piece by piece.
So let's zoom in on wind shear. The easiest way to picture this is to put your hands out, one on top of the other. Imagine your top hand is the fast wind way up high, and your bottom hand is the slower wind near the ground. Now, move your top hand forward faster than your bottom hand. See that rolling motion you'd create in the air between them? That's it. That's the invisible horizontal tube of spinning air. Now, inside that massive supercell, you have this incredibly powerful current of warm air blasting upwards. We call that an updraft. It's like a giant invisible hand. And this hand reaches down, grabs that horizontal spinning tube of air we just made, and yanks it upright. And just like that, you've now got a huge, vertically rotating column of air inside the storm. This is called a mesocyclone.
So we have our spin, but we don't have the speed. Not even close. A mesocyclone can be miles wide, and it rotates kind of slowly. So to get from that to a 300-mile-per-hour monster, the atmosphere uses a beautiful little trick that every single one of us has seen an ice skater use.
This is the key. This is the whole ball game. How do you take a wide, lazy rotation and concentrate it into something so narrow and unbelievably fast? The answer lies in one of the most fundamental rules of the universe.
It's a law of physics called the conservation of angular momentum. Now, I know that sounds complicated, but stick with me because the idea is actually super simple. It just means that the total amount of spin energy in a system has to stay the same. So if you make a spinning thing smaller, it has to speed up to keep that energy constant.
Think about that ice skater. When her arms are stretched out wide, she has a big radius, and she spins pretty slow. But watch what happens the second she pulls her arms in tight to her body. Her radius gets tiny, and to conserve all that spin energy, she suddenly whips around incredibly fast.
And believe it or not, that is exactly what a tornado is. It's simply the atmosphere pulling its arms in. A huge, spinning system is being forced into a much, much smaller space. So here's the magic moment. As that big, wide mesocyclone gets stretched downwards by the storm, its radius gets smaller and smaller and smaller. And just like the ice skater pulling her arms in, the air has no choice. It has to spin faster and faster and faster. This is how you transform a gentle rotation into a catastrophic, high-speed vortex.
Now, that mind-boggling wind speed is only half the story. Tornadoes have a second weapon in their arsenal, and this one is all about pressure. These two forces work together to create a devastating one-two punch.
You can actually see this next principle in action right now. Seriously, grab a flimsy piece of paper. Hold one of the short ends just under your bottom lip so it's hanging down.
Now don't blow at it, blow hard across the top of it. The paper magically lifts up, right? It defies gravity. So why does that happen?
The answer is a cool little concept called Bernoulli's principle. And all it says is that for a fluid, and yes, air is a fluid, the faster it moves, the lower its pressure. That's the whole rule. Fast air means low pressure, slow air means high pressure.
So let's apply that to a house. When a tornado roars over the roof, you have extremely fast-moving air on top, which creates a zone of really low pressure. But inside the house, the air is just sitting there. It's still. So it's at normal, much higher pressure. That massive pressure difference creates a powerful upward force, and the house literally blows its own roof off from the inside out. And how big of a pressure drop are we talking about here? In a really powerful tornado, the air pressure can be up to 15% lower than the air just outside of it. That might not sound like a huge number, but trust me, over the surface of an entire roof, that is more than enough force to tear a building apart. Okay, so let's put it all together. We have wicked speed thanks to angular momentum, the ice skater effect. And we have incredible lifting power because of pressure differences, Bernoulli's principle. Now we can finally understand how scientists actually measure and classify the raw fury of these storms.
This right here is the Enhanced Fujita Scale, or what meteorologists call the EF scale. It's basically a report card for tornadoes. It directly connects the physics, the estimated wind speed, to the kind of real-world damage we see. An EF0 might just snap some branches, but an EF5, with winds screaming at over 200 miles an hour, can literally scrape a house off its foundation, leaving nothing behind. So let's just recap the whole crazy process one last time. It all begins with wind shear creating an invisible horizontal spin. The storm's updraft grabs that spin and pulls it upright. Then the ice skater effect, conservation of angular momentum, squeezes that column of air, making it spin dangerously fast. And finally, Bernoulli's principle creates that low-pressure core, giving it the power to lift and destroy everything in its path. And this all leaves us with one final, really important thought. Understanding all this amazing physics isn't just a cool science experiment. Every principle we've talked about is a piece of the puzzle that scientists are using to build better and better predictive models. The more we understand the how and the why behind a tornado, the better we'll get at forecasting them, the stronger we can build our homes, and ultimately the more lives we can save from one of nature's most incredible and violent spectacles.